For this unit, we're going to talk a little bit about problems involving kinetic energy. So to start with, let's do a conceptual one. Imagine there's the captain of a spaceship, and he's going along and he's hauling cargo. And he has to choose two things. He can either haul twice as much cargo, or he can go twice as fast, and with the same amount of cargo. And he'll make the same amount of energy either way. But let's imagine that he has to pay for fuel. And the amount of fuel he uses is equivalent to the amount of kinetic energy he has at top speed. So let's think about this. Let's assume that if he's going slowly, he has top speed v, and he's going quickly, his top speed 2v. And if he has a light cargo, he's a cargo of m, and a heavy cargo, he's a cargo of 2m. If he gets paid the same either way, which one makes more sense? Which one's going to use less fuel? So pause the video and take a second and try to figure this out, and we'll go over it together. Okay, let's see what we've got. So let's try to figure out in general what his kinetic energy is. So his kinetic energy in the first case, it's 1/2 mv squared. That's just a general equation. However, in this case, m is substituted in for 2m. So this becomes 1/2 2mv squared, or mv squared. So that's how much fuel he uses if he takes heavy cargo, low speed. Now let's imagine he goes twice as fast, but with half the cargo. The general equation is 1/2 mv squared. So let's use the specific numbers here. 1/2, mass is still m, so just 1/2 m, times v squared. In this case, velocity is 2v, so 2v squared. 2v squared is 4v, so that's 4 over 2 mv squared equals 2v squared. So 2v squared units of fuel. So as you can see, just from the simple conceptual problem, it's easier to carry twice as much stuff as it is to go twice as fast. And that makes sense because the relationship between mass and kinetic energy is linear, whereas between velocity and kinetic energy is quadratic. So now that you have the basic concept down, let's do a slightly trickier problem. For this problem, first we're going to figure out how much energy it takes a 1-ton car, and we'll use a metric ton, which is 1,000 kilograms. How much energy does it take a 1-ton car to go from 20 meters per second to 30 meters per second? So be careful with your unit conversions here and see what you get. So let's start by looking at our general equation. As we wrote earlier, it's 1/2 mv squared. So we want to figure out what's the kinetic energy final, what's the kinetic energy initial, and then subtract the two of them, which will give us the change in kinetic energy. So let's write this out. We know mass is 1,000 kilograms. Velocity is 30 meters per second for velocity final, and velocity initial is 20 meters per second. And we know that joules, our energy unit of choice, is kilograms meters squared per second squared. So you don't have to do any unit conversions here. So let's plug it in. 1/2 times 30 meters per second quantity squared times 1,000 kilograms is 450,000 joules, whereas 1/2 times 20 meters per second squared times 1,000 kilograms is a simple 200,000 joules. So let's find the change in kinetic energy. Change in kinetic energy is the final kinetic energy, 450 times 10 to the third joules, minus 200 times 10 to the third joules, which comes out to 250,000 joules. So that's the amount of energy it takes the car to go from a slower speed of 20 meters per second to a higher speed of 30 meters per second. And you can use this for any two speeds you look up. And what you'll notice is there's a bigger difference between higher speeds, for instance between 90 and 100, than there is between lower speeds such as 0 and 10. And I invite you, if you want to make sure this is true, check that out, do the equations yourself, and then you're ready to move on to the next one.